All right, welcome. This is Carnegie Mellon 859 BB, Quantum Computation and Quantum Information. I'll put up here two leitmotifs for the course. First one is 10 to the 500 parallel universes. That's what we're going to kind of talk about in this lecture. And the second one is rotate, compute, rotate. And you'll understand what that comes to mean in the next lecture. Yeah, so to explain a little bit this first one, I have here a quote from David Deutsch, who's one of the two co-founders of quantum computing, together with Richard Feynman. It's from his book called The Fabric of Reality. And he says, quantum computing is nothing less than a distinctively new way of harnessing nature, which I think is true. And he goes on to say, it'll be the first technology that allows useful tasks to be performed in collaboration between parallel universes, which sounds pretty grandiose. I don't know how I feel about that comment exactly, but it's pretty cool, right? I mean, it sounds like something worth learning about at least. So yeah, in the first part of this, in this first lecture, I'll kind of tell you a little bit about that and kind of the excitement, the mystery, the potential power of quantum computing, how cool it is, what kind of strange concepts it involves. And at the same time, I also want to convince you that it's not that complicated. You can learn it. It's just like a little bit of a twist on basic computation. So that's what this second leitmotif will be about. OK, so quantum computation, quantum information, what is it about? Let me draw a little Venn diagram here about this topic. So this is physics. Luckily, there's only three things here, so I can make a nice Venn diagram. This one is math. This one is computer science. OK, so quantum computation is right in here. It's a topic that's at the center of these three things, physics, math, and computer science. And right here is me. That's me. Oops, can't spell my own name. So as you'll be able to see once I move, I put myself at the intersection of math and computer science. I'm a theoretical computer scientist. And honestly, I really don't know that much about physics. I don't say that with pride. I say it with a little bit of embarrassment. But it's true. I imagine the majority of you know more about physics than I do. I'm trying to learn. But I say this to point out that you don't actually need to know physics to do quantum computation. And we'll see a little bit about that at the end of the class as well. But you can really do it without exactly knowing any physics, just taking the sort of the mathematical rules of quantum mechanics, which I'll tell you about, and applying them to computation. And that's sort of the perspective we'll take in this class. And it'll have the biases of me, a theoretical computer scientist. So in particular, throughout most of this class, we're going to be looking at quantum computation from the perspective of this area called computational complexity. Or it would probably be better if it had been called computational efficiency. So the kinds of questions that we're going to ask ourselves in this class are like this. And one is, are quantum computers, if they're ever built, more powerful or more efficient than classical ones? This is a good time to emphasize that about 1 million times in this course, I'm going to say the word classical. And classical is just an adjective that means opposite of quantum or not quantum. OK, so classical computers just mean regular, normal computers, such as you're used to. And so I'm sure you've at least heard a little bit about quantum computers, the potential for quantum computation. But one thing that we don't know for sure is whether, when they're built, whether they'll actually be more powerful than regular computers. We believe they will, but this is one thing that we'll take up in the class. So if they are, one thing that we kind of want to know is well, for which problems or tasks, be they computational or having to do with information theory or communication, are they more powerful for? OK, let me just end the question there. Okay, so we know some things that quantum computers should be better at classical computers at doing, but we don't exactly know the exact power, what exactly delimits their power, and what they should be good at compared to classical computers. So we'll think about that in this course. And finally, especially towards the end of the course, I want to talk a little bit about like near-term prospects for actually demonstrating this potential superiority. And in fact, we don't have to wait for some of these things. There's some tasks, particularly related to communication, like quantum key distribution, where we don't have to wait. We already have commercial enterprises that will sell you quantum-based key distribution, which is in some sense provably more secure than classical versions of such. Okay, so this is a perspective that we're going to take throughout the course. And so therefore, I want to spend a little bit of time now talking about this notion of computational complexity and efficiency to get you warmed up for the sort of questions that we'll address in the course. And for particular, what I'm about to say applies both to quantum computation, classical computation, whatever. I just want to get used to the concept of efficiency, resource usage, running time. How can we judge what kind of algorithms are efficient enough to run in the real world and which ones are so inefficient that you could never run them in the real world. Any questions, by the way? In general, you can feel free to just stop me. You don't have to put up your hand. Just say a question. Okay, well, I haven't really said anything yet, so. Great. So I want to talk about, for a little bit, about a distinction between what I'll call physical versus unphysical numbers. Okay, so if you know a little bit about theoretical computer science, basically I'm going to be getting at big O notation and the distinction between polynomial and exponential, but I'll try to do it in a way that's less theoretical and more vivid, I suppose. So I say numbers. What is the point of a number? It's to count something, right? It's to count objects that exist in the physical world. So for example, 10 is a popular number. It counts the number of fingers you have on your hands, typically. Okay. Great, so that's 10. 100 is another popular number. So 100 is 10 times 10. If you build a wall in Minecraft that's 10 blocks wide and 10 blocks high, then you need 100 blocks. So, okay, that counts some simple object. How about 1,000? Still a very small number. I mean, I'm sure you've been in a room with 1,000 people before, so that's no big deal. Also, I'm a computer scientist, so I mean, to me, 1,000 is nothing more than 2 to the power of 10. So I prefer to view it that way. Normally, we count in bits and powers of 2 in computer science. Okay, of course, it's actually 1,024, but it's basically the same difference. Right. Okay, let's step it up a little bit and go to 1 million. Okay, so 1 million is a pretty big number.
That's the number of dollars you have in your bank account.
It's the number of dollars in what?
You have in your bank account.
Oh, I wish. I could come over to your place. Right, so this is 10 to the 6, or 2 to the 20. It is a physically plausible number, though. I mean, it's a little bit hard to imagine, but not that hard. So, for example, it's the number of people in Pittsburgh, maybe. 1 million seconds is 11.5 days. So that's not that long. Actually, I have a picture I want to show you just to illustrate that you can physically count things. I got this great book called How Many Jelly Beans? It's really great. I love this book. Yeah, so I hope this is computer generated, by the way. This is a picture of 1 million jelly beans, supposedly. So if you squint at this, I'm not holding it very well, but there's a million dots in this picture apparently. So you can actually, here you go, pass it around. You can actually see it. Yeah, it's 500,000 jelly beans on the back.
Very passing, so it has to be coordinated.
Yeah, it's gonna, maybe it's Well, yeah. You can come look at it after class. All of which to say, I also kind of tried to estimate, like, I think 1 million jelly beans would fit in a car. So I think, 1 million is like a very reasonable number. But, see, now we're getting a little bit, I'm going to go to higher numbers next. And it's sort of, we're about to get into, genuinely big numbers, I think. So the next number I'll put up is a billion, which is 10 to the 9 or 2 to the 30. And that's pretty big. It's not so easy to get, like, a billion objects together. But, you guys are probably familiar with computers and computer science. It's not that crazy, right? I mean, so 1 billion bytes is a gigabyte. It's no big deal to have a gigabyte on your hard drive. So, I mean, in particular, it means like your hard drive in 1 gigabyte has like 8 billion little magnetized regions or something. I don't know much about electrical engineering or physics. So it's not so bad to have like a billion things. 1 billion seconds is 31.5 years, which is a lot. But on the other hand, like 1 gigahertz is like 1 billion times per second, right? And I don't know, I'm not exactly sure, but like I think a kind of a crappy cell phone can do, I don't know, 1 gigahertz or like 1 billion instructions per second. So from the point of view of computing, it's not so unreasonable to, I don't know, do 1 billion instructions. Okay. Of course, we're going to keep going up here. So the next one is 1 trillion. That's 2 to the 40. Now it's getting a little bit serious. I mean, like 1 trillion seconds is 30,000 years. That's a lot. You can have a 1 terabyte hard drive, but it's getting up there. I guess like 1 trillion is like maybe like the number of flops for like a PlayStation. The number of floating point operations it can do per second. So you can still do a lot of operations. Maybe I got that a little bit wrong. I was just looking stuff up on Wikipedia. But it's roughly in that neighborhood. But this is definitely, if you've ever done computer programming, where things are going to get serious, right? Like you don't go around like doing a for loop for I equals 1 to 1 trillion, or you don't like allocate an array of size 1 trillion, right? It just gets a little serious if you're going to do stuff like that.
GDP of Florida.
GDP of Florida? Oh, somebody's got Wikipedia right there. Or knows a lot about Florida. Okay, the next one is 2 to the 50. I don't even know what the name of that is. But that's like 1,000 times bigger than this one, right? So it's like 1,000 trillion. So like 1,000 1 terabyte hard drives is a lot. Or maybe you could have 50, 20 terabyte hard drives. All right, let's keep going. 2 to the 60. That's 1,000 of these. So I guess it's like 50,000 20 terabyte hard drives. That's pretty big, right? Like that's like a, like a data center that like, I don't know, like a Google or the NSA would have or something. I also apparently looked this one up too. That's like the number of floating point operations per second for like the world's fastest supercomputer, apparently. 2 to the 60. And so it's a lot, but if you have a supercomputer, maybe you can do like that many instructions per second. Let me also put this one up, 2 to the 64. That's a very popular one in computing. It's only, a little bit bigger than that one, 16 times bigger. But what is this? This is actually the number of different memory locations that your like computer here can address into. So that's plenty, right? I mean, we talked about how like this is bigger than like the world's biggest data center or something. So it's 2 to 64 is like enough to cover it. That's good. And actually, another thing that I wanted to point out, which is quite important, is that like to write down this number is tiny. It's only 64 binary digits long. Okay, so to write down 64 binary digits, or to name like a memory address in like an enormous data center like this, that is no problem. You can write down that on a piece of paper. But the actual magnitude of the things that's counting is like super duper enormous. Okay? And so if we go back to this, like it's like counting some objects. These are numbers which can conceivably count things which exist in our like physical world. Okay? Let me just like skip a few and go up to like a very large quantity, like 10 to the 50. Okay, 10 is like 2 to the power of 3, kind of. So this is like 2 to the power of 150, maybe. So that's very big. I mean, this is like if you took like billions and billions of the world's fastest supercomputer, and they operated for like the age of the universe, then they could maybe do this many instructions. Okay? So that's really like kind of an upper limit on like the most amount of computing or like the most imaginable physical objects that you could ever conceive contributing to like a computation. Okay, I also looked this one up. Some physicist estimated 10 to the 80 as like the number of elementary particles in the observable universe. Okay, so this is really like the upper limit of what I'd like to term, this brace will have to serve, physical numbers. Okay? Like numbers that can like actually conceivably count some object that's like occurring in our physical universe. Okay? And one can contrast this with, you know, well, what one might call unphysical numbers. For example, to pick one out of a hat, 10 to the power of 500. Okay, so this is a number which is like so enormous in magnitude. This is not like counting any quantity that exists in the, or ever could exist in the universe. In particular, from the point of view of computational efficiency, like if you have an algorithm that's going to run in this many steps, then it's useless. It will never run in the actual universe in which we live. And just emphasize one more time, you know, 10 to the 500, or like a number with 500 digits. To write that number down, it's okay. I can do that. I can write this number down in like 5 minutes on a piece of paper. It would be a drag, but I could do it. But it would just be like a string of digits, which is not corresponding to like a number that's actually counting some physical quantity. Oh. Any questions? Yep.
Technically, if you subscribe to multiverse theory, then it is counting some numbers.
Maybe. We'll get to that. We'll get to that when we discuss this a little bit for laughs, which is we will. Okay. So, having said all that, I do start to want to talk a little bit about computation and computational efficiency. And in particular, I'm going to talk about computation on such enormous numbers. So let me write down right now just something that I'll call a computational challenge. Computational challenge number one. Computational task number one. It's a pretty simple challenge. I want to multiply two given 500-digit numbers. Okay? So I want to think about like a computer program or a circuit, a piece of code that solves this problem. Takes in two 500-digit numbers and outputs their product. Now, having specified this challenge, like one thing you might ask is like, why would I ever care to do this challenge in real life? What possible reason could I have for wanting to multiply together two 500-digit numbers? Okay, because as I just kind of tried to illustrate to you, like, you know, it's not like you're building a wall in Minecraft where like the width is like, you know, 500-digit number and the height is some 500-digit number. You want to know how many like blocks you need. You're not trying to like, I don't know, like figure out what shape rectangles you can make that have like this many dots in them. These don't correspond to real quantities. So that's why I call it a computational challenge. Let's just say, never mind why you would actually want to do this in the real world. Let's just think about how you would program a computer or build a circuit to do this task. Now, one thing you might say, if you literally were sitting there in front of your computer and you had to multiply two 500-digit numbers, you say, well, my computer has this like chip in it that has like a multiply instruction. So why can't I just not use that? First of all, it actually evades the question of how the chip is doing it. But you can't do that because, as I mentioned before, right, the chip, all the like, you know, instructions that your computer chip do operate with 64-bit numbers. And it has like, an instruction in it which will multiply two 64-bit numbers and give you the 128-bit answer in like 1 nanosecond or something. But these are not 64-bit numbers. They're 500-digit numbers. So, that's about 25 times as long, a 500-digit number, as will fit into like one register on your computer chip. So it's kind of like, the task of multiplying, for a human, two 25-digit numbers. Okay, so like, let me write down two 25-digit numbers here. And I'll just make this one so it's not too crazily long. And like, this is kind of the task that's facing you when, you're trying to write a computer program or whatever to multiply to such numbers. I should get my more spelling. Yeah, you got it? Whatever. Oh, I botched it. Well, that's good, actually. I'll put a random digit here. There's like the Shakers or something that are like really experts at making furniture, but like when they make like a beautiful piece of furniture, they like intentionally put a defect into it so that, because they think that the only perfect thing is God, so they want to make sure they do not intentionally try to make something too perfect. So I was trying to talk and write there at the same time, and I botched it. Anyway, right, so let's imagine that this is your task, how to multiply these two numbers. Well, you all know how to do it, right? I mean, you learned an algorithm in grade school for doing this. There is an algorithm for multiplying two numbers. I'll sketch it for you in a second. But I just want to say that this is a task that needs an algorithm. Right, so you know how to do it, right? You do like this digit times this digit, and it's 25, and you put a 2 here, and then this digit times this digit, and add this, it's 22, and do this times this, do this times this, and so forth, and you write like about 25 digits, maybe 26 digits. And then you go back here and you do 2 times 5, that's 0, this is 1, and 2 times 8 is 9, and 2 times 3 is 6, and you do like another bunch of digits. And it extends like one digit further. And then you do it with this one, and this one, and this one, and this one. You get all the way out to this one, so it's way down here, below the part where the camera can see, but it doesn't matter because you know what I'm doing here. It stretches way out here, and then you add them all up, and you get the answer down here. Okay, and that's what a computer will have to do if it wants to do this multiplication. It's very annoying these days because like everybody's favorite programming language, Python, like has like the built-in ability to just multiply two arbitrarily long numbers, and so like you can't use it as a good example. But if you were trying to do this in C, for example, you would have to write like a 10-line program to like solve this problem. Okay, so computational efficiency and computational complexity is concerned with understanding how many steps like an algorithm takes. Okay, so if this is, I did it with an illustration with 25-digit numbers, but if you're doing, this algorithm on 500-digit by 500-digit multiplication, how many steps does it take? Well, you have to build this big tableau of numbers. Each line is like 500 to 1,000 digits long. There's about 500 to 1,000 digits. So, 500 times 500 steps at least. Maybe on the order of like, 1 million steps. Approximately 500 squared, or approximately 1 million. I'm not going to be too careful about this. Steps. Okay, and that's fine. Your cell phone can easily do that in 1 second. Great. But in general, computational complexity, we're concerned a little bit more with just than just, what if there's 500 digits in the input? You kind of want to know like how the number of steps the algorithm takes, or how the resources used by the algorithm scale as the size of the input scales. Okay, so in particular, if you use this algorithm, if it's n digits or n bits numbers, Then this like tableau of digits that you have to create will have about n rows and n columns, so there'll be about n squared digits. And so the number of steps will be, I don't know, to use physics symbols, proportional to n squared. Okay, for the theoretical computer scientists in the audience, we're not going to get like super excited about exact counting here. This algorithm, you know, takes a number of steps, which is roughly proportional to the square of the number of digits. And this is a good algorithm for us because this is a physical number. 1 million steps is fine. Okay? For example, if we wanted to multiply 1 million digit number times a 1 million digit, okay, so that'll be like a million squared. That's like 10 to the 12, which is like a trillion. Okay, so a PlayStation can do this in 1 second. So what I'm trying to say is, you know, for a reasonably physical size of an input, you know, you can write down 1 million digits on a computer. The answer will be 2 million digits, and like the number of steps it takes will also be like a physical quantity. Okay, so we call this a P algorithm. You can think of P as standing for physical if you like, or you can think of it as it actually stands for in theoretical computer science, polynomial. Okay, and that refers to the fact that this number of steps is a polynomial function of the size of the input. Okay. And in general, these are the kinds of algorithms we like because they can be executed, you know, in the physical universe. If I give you a million digit number, you know, the number of steps will be physically plausible. Any questions right now? Okay. Good. So that's one thing that computational efficiency and complexity is concerned with. Another thing it's concerned with is asking always, is there a better algorithm? So let's think about that. I mean, you know, this is fine, 1 second on a PlayStation, but we prefer it even faster, or better if we could. One might ask, is there a faster algorithm? And actually, if you never thought about this before, it might strike you as a funny question, because you might think that, like, almost by definition, there isn't. Like, you might think that, like, this is like the definition of how to multiply two numbers, it would seem, right? I mean, is there any other way to do it than multiplying them like this? Well, it turns out there is. The answer is yes. This was figured out by various people, but I'll tell you about what two people called Schoenhagen and Strassen discovered around 1970. They figured out a totally different way to multiply two really, really long numbers. And the number of steps it takes scales much better than n squared. It basically takes like n steps. This is like maybe a slight exaggeration. Actually, depends on the exact model of computation you used. Maybe you might prefer if I said n times log n steps. But basically, it takes proportional to n steps. I mean, a number of steps that's proportional to the length of the input. This is kind of amazing. It's almost like real time. Like just in the amount of time it takes you to like process the length of the input, you know, plus a little bit more, maybe another factor of 10 or 20 or 30. You can multiply two numbers, which is great, right? Because now, you know, instead of taking 1 second on a PlayStation, it takes, you know, like a millionth of a second. What is that, a microsecond? That's amazing, right? So, I mean, you can do this a million times, where before you could only do it 1 time in a second. So that goes to show that this is a polynomial time algorithm too. N is a polynomial in n. It's a better polynomial time algorithm. And we're interested in that kind of speed up. It can be great. Just an aside, you might ask how do they do this? It's a sophisticated algorithm. I'll just say one thing about it. The crucial aspect of it, crucial ingredient in it is, I'll just write FFT, the fast Fourier transform. It's an algorithmic ingredient, the key algorithmic ingredient in this super fast multiplication algorithm. And I wanted to mention it because the Fourier transform is also like a critical ingredient, if not the critical ingredient, in all super fast quantum computing speedups. So somehow the Fourier transform is right at the heart of quantum computation as well, as we'll see in the next lecture. So I wanted to give it a little mention here as well. Okay. So that's the story of one computational challenge, multiplying two super long numbers. Let me tell you now about computational challenge 2, which in some sense is the opposite challenge. It's the opposite of multiplication. It's the challenge of factorizing a given, or factoring a given 500-digit number. Okay, I'll give you a 500-digit number and work out its prime factors. Every number can be broken down into the product of its prime factors. Okay, so again, let me mention that this should be thought of merely as a computational challenge because, a 500-digit number does not actually, again, correspond to like counting anything in reality. It's not like you have 10 to the 500 tokens and you're figuring out how to arrange them into a rectangle, which is what factoring would be about. Just like a challenge. I give you a 500-digit number. The challenge, find its prime factors. So let's talk about this one as well. Just so we're all clear, right? Like if the input is like 91, and the output, anyone? Yeah, 7 times 13, I think. So again, okay, and the output is some 500-digit number. Okay, then it's a bit more serious. Well, we can repeat the same thing we repeated before, right? Like, what's an algorithm for doing this? We can recall the algorithm that we learned in 3rd grade, or I don't know, maybe it's 4th grade, 5th grade, some low grade. When they teach you how to find the factors of 91, what do they tell you to do? Well, you first check if it's divisible by 2. And that's pretty easy, right? I mean, maybe it takes like one step. You check if the last digit is even or not. Okay, and then you check if the number is divisible by 3. Okay, you could just, divide 3 into it, or if you know this trick, you can like add up all the digits. Okay, so maybe this will take like 500 steps or so. Okay, and then you can check if the number is divisible by 5. I guess you may as well skip 4. Once you know it's divisible by 2 or not. Actually, let's slightly change the problem. Instead of trying to find the prime factorization of the number, let's just try to find one factor of it. It's basically a similar problem. Okay, and I guess if it's written with digits, this is also easy. You can check if the last digit is 0 or 5, but if it's written in base 2, then it's maybe annoying again. But you just have to divide by 500, or divide by 5, so that'll take another 500 steps. Okay, and then you can check if it's divisible by 7. Yeah, there's really nothing else to do but run the little algorithm for dividing by 7. And you can do 11 and 13. At some point, I started listing primes here. At some point, it's like more trouble than it's worth to check if the divisor is a prime number than it is to just go ahead and divide it. So at some point, you'll probably just start dividing by all the odd numbers and seeing if it's really a factor. Okay, so you'll do that for a while. And if you're unlucky, or if somebody set you a particularly devious challenge where the prime factors are all really large, you might have to do this algorithm for many steps before you find a prime factor, or maybe decide that the number itself is a prime number. So in fact, what should you go up to before you can either find a prime factor or be satisfied the number is prime? Yeah?
The square root.
Yeah, you can go, you don't have to go all the way up to the number itself, right? You can go up until, check divisibility by a number which is around the square root of your target number. Okay, so your target number is 500 digits long, so it's somewhere in the neighborhood of 10 to the 500. Okay, so that's 10 to the 500 to the power of a half, so that's 10 to the 250 or so. So you might need about this many trial divisors. Now the fact that each one is taking you 500 steps is not really a big deal, because overall you're going to be doing like 10 to the 250 operations. Well, hypothetically you would be if you were going to actually execute this algorithm. But the point is, this is a completely unphysical number, right? I mean, it's more than the number of Planck times since the age of the universe times the number of elementary particles in the universe, et cetera, et cetera. So I mean, you can never execute this algorithm. It'll never finish. Yeah, so that's a bummer. That's a shame. Just emphasize, right? This is like not physical number. In fact, this is like not a P algorithm. Okay, in general, I mean, I picked the number 500 here, but in general, if it's like you're factoring an n-digit number, okay, then the number of steps will be like maybe square root of 10 to the n. Okay, just maybe like 3 to the n or so. Okay, and the point is that this is not a polynomial function of n. This is an exponential function of n. Which is why this is not a practical algorithm. Okay, well, that was just one algorithm, the algorithm that they teach you in 3rd grade for factorizing. And, there's a faster algorithm for like multiplication. Maybe there's a faster algorithm for factoring a number. So again, we should always ask ourselves, is there a faster algorithm? And actually, again, the answer is yes. Although let me delete this exclamation mark and just convert it into a period. Because there is a faster algorithm, but it's like not that much faster in some sense. So this is just for the sake of your culture. The fastest known algorithm for factoring is due to Pollard from 96. And I'm going to say something that's like a little bit like wrong, but you should think of it as like maybe factors an n-digit number, and think of it like 1,000,000 to the power of the cube root of n. Okay, I mean, if you want to know the truth, it's exponential and the cube root of n times some like polylog factors. Also, you really, really want to know the truth, it's only conjecturally like this fast, depending on some number theoretic assumptions, but like, okay, in practice, it'll be something like this, okay? And so this is better. It's not like, 3 to the n. It's like, well, debatably better. It's like 1,000,000 to the cube root of n. But even though this is somehow in principle faster, it's still exponential. This is still not a P algorithm. It's still like not feasible to execute this algorithm on a 1,000,000-digit number in the way that it was totally feasible to execute the algorithm for multiplying 2 1,000,000-digit numbers. Okay. So this is a very hard challenge, and I'll mention a teeny bit more about it in a second, but if you know a little bit about cryptography and this RSA encryption scheme, RSA is some scheme for encrypting things, and it's related to factoring. And because of this company RSA put out a bunch of challenge numbers, like really long numbers, and they offer like prizes for people to factor them. And the most recent factored one was a number called RSA 230. That's called because it's 230 digits long. Okay, and it was factored, so this came out in like, they published this in, I don't know, the 70s probably, and it was factored 3 weeks ago. I think it's actually not the longest one that's been factored. I think a slightly longer one was factored like 2 years ago. But anyway, this is the limit of what they can do now. This person who did it 3 weeks ago, it took like multiple machines running for like multiple years to factor this one number. And you have to look at the graph of like, the longest, RSA challenge number that's been factored over time. Like it goes up very slowly. So like this is, We've still got a long way to go even to get to like 500 digits. And in fact, this is going to be likely impossible unless there's a huge advance in algorithms. So for example, there's another one called RSA 1024. This one is 1024 bits long. It's a little bit weird how they name some of these things. Okay, so this one is longer than this one. This one's like 700 and something bits long. And this one, if you can factor it, it's worth $100,000. And you know, based on how things have been going over time, and like the state of our knowledge of factorization algorithms, perhaps if like Google and NSA like teamed up to put like all their computers together to like work on factoring this for like some decades, like maybe this is within reach. But there's like RSA 2048, which is 2048 bits long. And yeah, you actually only get $200,000 for this one. But this one's like totally out of reach. It's like impossible. Like, in other words, if you, well, without a breakthrough in an algorithm. So if you just use this algorithm, you know, then the number of steps it would take to factor this number is some completely unphysically large number that could never ever be done in the universe. Well, as I said, that's actually only if you use the known algorithms. And, you know, algorithms is a major area of research. So it could be, in fact, that there is a better algorithm for factoring. Even a much better algorithm for factoring. Let me just summarize the situation with what we know with this statement, which is just that nobody knows, you know, a P algorithm for factoring. And you can ask a further question is, well, is there a P algorithm for factoring? Maybe we just don't know it. Maybe there isn't one. That's an interesting question. I guess the majority of people who thought about it a lot guess that there isn't. And in some sense, not everybody, but the majority of people do. And in some sense, all of us put our money where our mouths are, kind of bank on this fact. Because the assumption that there's no physical algorithm for factoring, let's say 2048-bit numbers, is at the heart of like most cryptography, almost all cryptography that's in use today. So, yeah, first of all, you might ask, like, what does factoring have to do with cryptography? I mean, probably you've heard the story, but the point is this. What have we just seen? We saw that there's like one task, multiplication, which is, I'll put, say, easy, okay? It's not really a problem to multiply enormous multi-digit numbers. On the other hand, sort of the quote-unquote reverse operation, factoring, seems to be hard. Okay, it seems totally impossible, as far as we know, to like factorize, you know, to give an algorithm that factorizes 2048-bit numbers. And this teeny little picture, this is really a cartoon, but this teeny little picture is exactly what you're looking for in life in cryptography. Okay, so in cryptography, what you know, at high level, what you want is you want a system of, let's say, encrypting secret messages, where, you know, the task of encrypting the messages is easy because you want to do that over and over. But conversely, you want that decrypting is hard. The whole point is that nobody should be able to decrypt your secret messages. Okay, so in the 70s, you know, computer scientists already noticed that multiplication and factorization have this kind of property, and they built cryptography schemes like the RSA scheme that are based on this. And the security of the scheme is based on the presumed unphysicality of factorizing such large numbers. In fact, you know, every time you like go to any web page these days, like more than likely than not, it starts with HTTPS, and the S stands for secure, and that's because it's like using RSA in it. So like literally every time you go to a web page, you're relying for security on the assumption that this is like an impossible task. Great. Well, remember this course about quantum computation, and I guess you probably all, or almost all of you, know what the punchline of this long story is. Which is that in 1994, a person called Peter Shor, he gave a P algorithm for factoring on a quantum computer. Okay, so again, as you probably know, a quantum computer is like a hypothetical device, which we haven't really built physically yet, but it's a hypothetical device that's like a computer based on the very sound and long-standing principles of quantum mechanics, for which there's no theoretical impediment to building such an object, but it seems like a great engineering challenge. We'll talk about this more throughout the course. But people got to studying the potential power of such things, and this is like the most dramatic demonstration of their power that has been shown before or since. So Shor actually showed that factoring actually becomes an easy task, and we do know a P algorithm if you had a quantum computer. Okay? So this made people really excited about quantum computing. People understood that if you could actually build a quantum computer, you could break all messages encrypted with RSA. You could break all or decrypt all message previously encrypted with RSA. So all previously thought to be secure messages could be decrypted, and so forth. So this made people very excited about the possibility of a quantum computer. Let me also just mention, just so we know what we're talking about, his algorithm takes roughly n squared steps. Okay, maybe there's like a log factor or something, but n squared steps to factor an n digit number. Okay, so if you had a quantum computer that had as much processing power as like a random cell phone, then you could do this $200,000 task in 1 second. Okay, so that's pretty awesome sounding. So how does he do it? I mean, how is it possible? How can you do this task, which is seemingly intractable on a normal computer? Well, we'll see. I mean, by lecture 12 or something, or lecture 9, you will know how to do it. But let me just say, at the highest possible level, it's a quantum computer. It relies on the laws of quantum mechanics, and it uses a basic fact in quantum mechanics. I guess I'll start using these abbreviations since quantum mechanics. Which is that, if you're given, let's say, 1,000 subatomic particles like photons or electrons, the kind of things to which the laws of quantum mechanics apply, they have a joint state. I'll say some words about it in a second, but just like in normal physics, if you have like a hockey puck sliding on a sheet of ice, its position, its state, is defined by two real numbers, the x-axis and the y-axis. Or if you have a ball flying in space, its position is specified by 3 real numbers. Or if you also incorporate its velocity, then it has like 3 position numbers and 3 velocity numbers, that's 6 real numbers. Well, quantum mechanics tells us that if you have 1,000 photons and you're interested in the joint state of their polarization, whatever that is, then their state is defined by a bunch of numbers. And it's like 2 to the 1,000 numbers. 2 to the 1,000, I was going to say real numbers, it's actually complex numbers, but whatever, numbers. These numbers are sometimes called amplitudes. We'll see all this terminology properly when we get into quantum mechanics for real in a lecture or two. But this is, an inkling of how this is possible. It's perfectly feasible to get 1,000 particles together. That's no big deal. 1,000 photons is not a lot. But the state of those particles is apparently encoded by 2 to the 1,000 numbers, which is kind of extraordinary. And furthermore, let me write this here, just to somehow emphasize it, nature seems to store these numbers. Okay, so in whatever way nature keeps track of reality, it's storing these 2 to the 1,000 amplitudes that define the state of these 1,000 photons. And there's like thousands of experiments that have physical experiments that have been done over the last century that really confirms that this is the way nature works. So that's kind of amazing. And to comment on this a little bit, in some email I pointed you to the video lectures of this quantum computing expert called Umesh Vazirani. And he says something at the beginning of those lectures which I like a lot. He says, quantum computing is about trying to hack into nature's computer. I mean, so if nature somehow is storing 2 to the 1,000 numbers, wouldn't it be amazing if we could somehow get these 1,000 photons together, put them through a little obstacle course with mirrors and beam splitters and so forth to manipulate their state and somehow extract some computation out of these 2 to the 1,000 numbers that are somehow being stored. And really that's what quantum computation is about. As we'll see, it's not so easy to extract that information out of these 2 to the 1,000 numbers that are sitting there. But it gives you an inkling, this description of what's possible. Actually, to make it sound even more exciting, this one co-founder of the field of quantum computation, David Deutsch, who we got this quote from, he thought that Shor's algorithm is like a dramatic illustration of the existence of parallel universes. Okay? In fact, of 10 to the 500 parallel universes if you're factorizing 500-digit numbers. So let me read a slightly longer quote to you from his book. It says, when a quantum factorization engine is factorizing a 250-digit number, the number of interfering universes will be of the order of 10 to the power of 500. This staggeringly large number is the reason why Shor's algorithm makes factorization tractable. Deutsch said earlier in his book, that the algorithm requires only a few thousand operations. Actually, it's probably a little bit mixed up there. It's more like maybe a few million operations. But whatever, 1,000, a million, those are small numbers. I meant, of course, a few thousand parallel operations in each universe that contributes to the answer. All those computations are performed in parallel in different universes and share the results through interference. So that's a pretty grand-sounding statement. It's pretty cool, right? I don't know. So let me talk about this a little, and then we're getting into fuzzier stuff. So here, Deutsch is referring to a so-called interpretation of quantum mechanics, which I'll write the name of on the board. He's referring to the so-called many worlds interpretation of quantum mechanics. And well, let me finish writing, but I should emphasize that the word interpretation here is important, because it's more about philosophically how you interpret this kind of amazing fact of physics. Not so much about actual mathematics or computation itself. Many worlds interpretation. It's an interpretation of the laws of quantum physics due to a person called Hugh Everett from his PhD thesis, which was in 56 or 57. And as I said, this is almost like a philosophical concept. So I'm telling it to you kind of in this first lecture, kind of for fun, kind of to make it sound exciting. There are a lot of philosophical questions surrounding quantum mechanics. I mean, this seems rather extravagant that the state of some handful of particles would be defined by an unphysical number of numbers. And there's also an issue of quantum mechanics you've probably heard of. We'll see it more in upcoming lectures where these particles have the property that they exist in this extravagant state with 2 to the 1,000 amplitudes, but then when you measure them, they quickly switch to having only one state, and then that sort of fundamentally changes their state. And there's a lot of philosophical questions about what exactly it means to measure, and how does the particles know if it's being measured, and so forth and so on. And so kind of philosophers of science and quantum physicists themselves have tried to make some kind of philosophical sense of this. And one interpretation they have is this many worlds interpretation, which posits that these 2 to the 1,000 numbers are stored in 2 to the 1,000 parallel universes. Now, first of all, on one hand, it's a minority opinion, I think. But I don't say that in a derogatory way. I literally mean less than 50% or something. It's not a very tiny minority. It's a minority opinion, but it's some respected people have this opinion. So I mean, Deutsch, for example, fervently believes in this position. And it's certainly also like the most mathematically elegant and like compelling interpretation of quantum mechanics. So like actually like computer scientists and mathematicians kind of tend to like it a little bit because it's like very elegant, although it seemed extravagant in that way. And again, you don't actually need to know any like philosophical interpretations. You don't need to take an opinion on whether there are parallel universes or anything in order to study quantum computation. And we won't do so really in this course. But in the first lecture, I wanted to tell you these things for a little bit of fun. So in fact, I want to tell you a little bit more about this Hugh Everett person, just for kicks. So yeah, he was a PhD student in the 50s. Actually, he got his master's with a person called Ticha. He's a mathematician, but kind of like a proto-computer scientist, maybe. His master's thesis was about military game theory. And I say proto-computer scientist because like one of his PhD students was this famous Marvin Minsky, who's like sort of a founder of AI. One of his PhD students was like Manuel Blum. It's like a very famous Turing Award-winning computer science professor here at CMU. One of his students was Umesh Vazirani, who's this quantum computing expert. Oops. Whose lectures you might have seen. And this person also had a few like famous and not so famous descendants as well. So his PhD advisor was Wheeler. Wheeler was like a super famous physicist. I mean, super widely acclaimed, very famous physicist. Popularized the term black hole and did all sorts of things in physics. Yeah, this was his master's. This was his PhD. That was about the many worlds theory. He had also many other famous PhD students, many famous physics PhD students, including Feynman, who was the other kind of co-founder of quantum computation, together with Deutsch, this 10 to the 500 parallel worlds person. Also Griffiths. So Griffiths was a PhD student, got his PhD in early 60s, then became a professor of physics at Carnegie Mellon University until 5 years ago. And he's now retired, but he comes in all the time. You'll see him around. He's a very cool guy, has PhD students. Yeah, so he's a quantum computing or quantum physics expert around CMU. Right, but back to Everett. So he, in his PhD thesis, proposed this philosophical interpretation of, the facts of quantum mechanics, and it was, I guess, totally scorned by like all physicists at the time. They thought it was kind of wacky. So then he kind of left quantum mechanics. After he published his PhD, he went to the Pentagon and like did computer modeling of nukes, and then he got into operations research, and then he became a computer consultant. So you see, everybody kind of tends towards computing, which is nice. Yeah, but then in the 70s, his ideas kind of got revived. There's a physicist called Bryce DeWitt who became like interested in ideas and started promoting the many worlds interpretation, and got Everett to give some lectures, and Deutsch went to the lectures, and he got also very enamored with this interpretation, and that's how the idea kind of spread. Yeah, so that's a little bit about Everett. Yeah, this is academic genealogy. He also had like a real-world genealogy. This person who typed his PhD thesis was called Nancy, and then he married that person. And then they had a couple of kids, one of whom was named Mark, which is a very tasteful name for their son. This guy, Mark Everett, is also known as E. It's like he fronts this band Eels. It's probably from before you're born, but you remember this band called Eels? The Novocaine for the Soul song? Well, anyway, I would sing a little bit, but this is going to be on YouTube, so I don't know if they would consider it fair use. They'd probably immediately make me delete it. Yeah, so an interesting character. Okay, so that's, as I said, I tell you this a little bit for fun. I mean, seems kind of grand and amazing and freaky to think about 2 to the 1,000 or 10 to the 500 parallel universes. So if your soul is a little shaken by that, then let me just mention once again that like you don't have to understand or like believe in this interpretation in order to do quantum computation. And in fact, what I want to get into, especially in the next lecture, is this phrase, which I'll explain in a moment. But it's all about the opposite kind of mental states. The state that thinking quantum computation is like not too complicated. It's just basically a twist on regular computation. Mortals can understand it. So let me say a few quotes here that I thought were relevant. So this guy Feynman, he has a lot of famous lectures. In one of his lectures, he famously said, it's safe to say that nobody understands quantum mechanics. Which I think he really just meant this philosophical question of interpreting quantum mechanics. I think it's safe to say that nobody agrees on like what the grand philosophical meaning of it is. But on the other hand, the mathematics of it are simple. There's no problem. In the end, it's just some math. And that reminded me of another quote by von Neumann, who was like the founder of the mathematics of quantum mechanics. And he has a famous quote which I like, which is that in mathematics, you don't understand things, you just get used to them, which I think is really true. So I think over this course, you'll learn a little bit of math, and it takes a little while to get used to it. It's like linear algebra mainly is the main tool you need to do quantum computation. But I think once you get used to it, then you should find that it's not so hard to do quantum computation, I hope. Good. So in this course, that's what we're going to do. The next lecture is going to be a little bit of, again, high-level stories about quantum computing, and a little bit like what is the main power that quantum computation has over classical computation. And then we're going to talk a little bit about the mathematical basics of quantum mechanics. So that's some math stuff, some linear algebra stuff. And then we'll actually also spend some time just playing around with like the basics of quantum mechanics from the point of view of computation, what you can do with 1 qubit, what you can do with 2 qubits. And we'll see some interesting topics like quantum teleportation and quantum key distribution, quantum money, Bell inequalities, fun stuff like this. And then we'll get into quantum computation, like what you could do if you could actually harness 1,000 qubits together. We'll see the model of quantum computation. We'll see some basic algorithms in quantum computation. We'll see Shor's factoring algorithm and the other very famous quantum algorithm, which is the Grover search algorithm. And actually, at that point, we'll only be halfway through the class, so there'll still be plenty more to do. And we'll get to talk about quantum information theory at some point, learning quantum states, communication, relationship to quantum computation. And then towards the end, we'll talk a little bit about quantum error correction and the potential demonstration of quantum supremacy in the near future. Right, so let me end a little bit about talking about Shor's algorithm from the less extravagant viewpoint of, harnessing the power of 10 to the 500 parallel universes and a more prosaic point of view. Okay, so Shor's quantum computing algorithm for factoring was published in 1994, and it was directly based on an earlier quantum computation algorithm developed by a person called Dan Simon. And he had an algorithm called Simon's algorithm. And this was also published in 1994 in the same conference as this one, but it was actually, I think, around for a while before that, but it was like rejected from conferences. Because I think at that time, computer science people thought this like quantum computation was totally crazy and like obscure, and most people didn't want to hear about it. Of course, once Shor came up with this, they really had to take it seriously. But a few people were thinking about it, in particular Simon. And Shor directly says, and we'll clearly see in the course, that like his algorithm is directly based on Simon's algorithm. So Simon was a graduate student at the University of Montreal. His advisor was a guy called Gilles Brassard, who was one of the influential early figures in quantum computation. And Simon, I guess, was interested in cryptography for his PhD thesis. And at some point, Brassard was just like, why don't you look at this quantum computation stuff? So he said, okay, and he looked at it. And he came up with this algorithm, this quantum algorithm that was very efficient at doing something. It did a very task of unclear value much faster than a classical computer could do it. So it's interesting, but it's not as dramatic as this one. But it's directly inspired, sure. And yeah, then he published it, and then I left academia. I'm not even totally sure he got his PhD thesis. Maybe somebody will tell me later. Yeah, he got interested in like networking and security, went to work at Microsoft, product group. I think he's still working at Microsoft. Yeah, so many years later, well-known quantum mechanics person, Fuchs, was very interested in this topic, Everett's many worlds interpretation. And so he kind of took a survey. He made like a questionnaire for like a bunch of famous quantum computing people like Shor and Deutsch and so forth. And he asked each of them, you know, when you were thinking of your famous algorithm, whatever it was in each case, you know, were you inspired by Everett's many worlds interpretation? And he wrote this to Simon, and Simon's response was, who's Everitt and what's his interpretation? And he went on to say the following. Simon said, I was approaching the problem purely from a computer scientist's perspective. I learned the absolute bare minimum of physics I needed to be able to understand the computer science question, which, as I saw it, was, quote, these crazy people are claiming that if you add these very weird yet theoretically physically implementable functions to a computer, then you should be able to do amazing things with them. Prove them right or wrong. I, meaning Simon, I'm continuing, I actually started out trying to prove that quantum computing was useless, and eventually narrowed down the difficult, unsimulatable part of a quantum computer's power to this, rotate, compute, rotate. He says that helped guide my search for a computationally interesting quantum algorithm. Okay, so in the next lecture, I wanted to bring up that quote to illustrate the point, which I mentioned before, that like you don't need to know physics to do this, and in some sense, you know, quantum computing, it has this amazing power, but you can boil it down to like kind of classical computing plus like a little bit more. And to spoil it a little bit, I kind of slightly spoiled it already. To spoil it a little bit, the one thing that the quantum computer can do, in some sense, is Fourier transform on a truly enormous amount of data, like a signal involving 2 to the 1,000 numbers. Somehow a quantum computer can do the Fourier transform on such a signal, and that's the source of its power. And a Fourier transform is actually just an operation on an enormous vector. In fact, it's just an enormous rotation on this vector, rotating it from one basis to another basis. And so at that level, that's like the prosaic way in which, you know, this boils down all the power of a quantum computer. Yeah, so we'll talk about that in the next lecture. And yeah, so I'll just close by saying, I mean, no, in preparing this course, you know, I was talking to my wife about, you know, how I should present things, especially in the first lecture. And, you know, I said on one hand, I want to get them like super excited, like quantum computing is amazing, there's a factoring algorithm, there's parallel universes, it's crazy, it's amazing. But on the other hand, like I want to get across the point that like, don't worry about it, it's just some math, like we'll all learn it together, it's not a problem. You know, which should I emphasize? You know, I don't want to be like too like out there or like too dry. And she's like, you should really emphasize the first part, like the craziness and the awesomeness, because you're too like low key overall. So, like don't like drag down their hopes and dreams like in lecture 1. So yeah, that's why I want to talk about like these things like parallel universes and many worlds interpretation and stuff like that in the first lecture. But I should emphasize that, you know, you don't need to know these things or to believe in these things or even to think about these things in order to understand like Simon's algorithm and Shor's algorithm. And you know, in the next couple lectures, what we'll get into is, you know, the actual practicalities and math of quantum computing. Okay, so I'll see you on Thursday.